Welcome, my dear students, this new session. In the last session, I introduced about the matrix inverse, and then we have to just say that how to find a matrix inverse, method of finding the matrix inverse. We using this method for finding the inverse is we have to matrix A, then write identity matrix from the same size, and then apply the elementary operation. We have to convert this matrix into the form of a identity matrix, and then we have some matrix B. Then clearly this B is nothing but is equal to inverse of A. Then B is nothing but is equal to inverse of A. If the system has a solution, then this is happening. If this system is not solution, then we cannot get a there is an identity matrix into a this form is this. Now in this class we try to discuss about the how to solve a linear system with the help of a inverse a matrix inverse transfer invertible matrices. If we have a, you know that any linear system can be written in the form of a Ax is equal to B, a form where A is a coefficient matrix and B X is the variables, and then A is nothing but is equal to, we have a alpha 1 1 up to alpha 1 n, then we have a alpha n1 up to alpha nn. This is a coefficient matrix. B is nothing but is equal to, you have a right hand sides, b1 up to bn, and x is nothing but is equal to, we have a variables x1 up to we have a x1 up to we have a xn. So any system can be, any linear a system can be written in the form of Ax into B is there. Now if we have a, this is the matrix, this is if this is a matrix, we have a coefficient matrix. If this coefficient matrix is invertible, then we can say that this x can be written in the form of A inverse B, and then we can say that this x can be written in the A inverse B. So we can find the inverse of A B and multiplied by B, we get the solution of this system of equation. Okay, so matrix inversion can be used to solve a certain system of linear equations. Recall that system of linear equations can be written in the single matrix form in Ax into B, and we know that A and B are the known and X B to be determined. So we just take assume that we have a, if A is invertible, then we can multiply both sides of this. So we have a Ax is equal to, we have a B, and if we have a is invertible, then we can say that A inverse of Ax is equal to B, and then by using the associativity condition, A inverse A x is equal to B, and then last time we have to show that if matrix is invertible, then there exists a matrix B such that A or B is equal to identity, and the same B is equal to A is equal, B of A is equal to identity, and also said that if this is equal to B is nothing but is equal to A inverse. So we can say that this can be written in the form of A inverse is equal to, we have identity, and the same as A inverse A also identity. So by this property, this is identity into x, we have is equal to B, and identity into, we have a x variable is nothing but is equal to x itself. So sorry, this is I'm sorry, this should be just this A multiplied by both sides by A inverse. So this is A inverse B, this is also showed A inverse B, this is also we have A inverse B. Okay, so this implies that we can say that x can be written in the form of A inverse B form. Then we can say that if we write x can be written in the form of A inverse B form, then we can easily say the solution of a given any linear system of equation. So if we find the inverse, then by the inverse of method we can easily find the if this matrix we have a coefficient matrix is invertible, then the inverse is exist, and inverse is exist means we can say that the solution of this given system of equation can be written in the form of x is equal to A inverse B. For example, we just we have just this thing. Now this gives the solution of the system of equation. Now if x is any solution, then necessarily x can be written in the form of A inverse B. So the solution is unique. Of course, techniques work only when the coefficient matrix A has inverse. So this way can be only work when we have this coefficient matrix A has an inverse. If the coefficient matrix is not invertible, then we cannot get the solution of any system equation by using this technique. Okay, so consider the system of equations. I will try find the first is we can find the argumented matrix. We have a this, and then we have a or just we can write the coefficient matrix of a this. We have coefficient matrix is 1, minus 6, minus 4, 2, minus 10, minus 9, minus 1, 6 and 5. Then we try to find the inverse. Then we can write A in the form of this identity matrix, and this is nothing but is equal to, we can write 1, minus 6, minus 4, 2, minus 10, minus 9, minus 1, 6, 5, and then we have a identity matrix of 3 by 3. Apply the elementary operation. This is, we have a provate element, and then with the help of this, we means you can say that R2 can be replaced as a R2 minus 2 times of a R1, and then R3 can be replaced as a R3 plus R1. So if we write this matrix 1 minus 6, you have a minus 4, and then you have 1, 0, 0, and then we have to just this minus 2 times of this is equal to 0. Then you have a 10 and plus 12, you have a 2. Then you have a 9 plus 4 to the 8, 9, so this is equal to, you have a minus 1, and you have a this is equal to, you have a minus 2, this is 0, and sorry 1, this is 1, and then you have a 0. Now you have to adding last and 2, this is 0, then 6 plus 6 is equal to, you have a 0, and this is equal to, you have a 1, and then you have is equal to 1, this is equal to 0, this is equal to 1. Okay, now we have to just take it in this. Now this is our pivot element. Now we have to write R2 can be written as a 1 by 2 R2. So this can be written in the form of a matrix in the form of a 1, minus 6, minus 4, 1, 0, 0. Now 0, 1, minus 1 by 2, minus ka 1 and 1 by 2, and then you have a 0. Now you have 0, 0, 1, and you have a 1, 0, 1. Now we have this is the pivot element here. Now with the help of this, we have to this R1 can be written as a R1 plus 6 times of a R2. So this matrix come into the form of a 0, 1, minus 1 by 2, and then you have a minus 1, 1 by 2, 0, and then the 0, 0, 1, 1, 0, 1, and then we have to writing this. This is 1 because R1 is R plus 0 is equal to, this is 6 is equal to 0. Then you have a R1 is equal to minus 4. Then you have a, and then you have a minus 4, and then you have a minus ka, this is 6 is equal to 3. So this is equal to minus ka 7. Then you have a 1, and then you have a minus minus 6, so you have a minus ka 5, and then you have a 0, 0 plus 6 by 2 is equal to 3, and then you have a 0 is this thing. Now with the help of this element, we can make here and here 0. So like this, I just say that into this form. Okay, this we just up to here we getting, and now we have to getting up to this one clearly, and now we have to just this is the 3 position. We take this position and then make a here 0. So I first stepping is this, then we have to getting into this form. Now we have a this position, and then we getting the this is 6 is again 0. So this means we have to this we get opting into this form. R1 can be written as 6 R2, then we have to getting is this position, and now this is clearly, you can say this is identity matrix, and then we can say that clearly we can say that A inverse is nothing but is equal to, this is the matrix is coming to, this is, we can say that this is our A inverse. Okay, now if this is A inverse, then you can just check we have a this our A inverse, then we can find this is our A inverse. So A inverse is equal to invertible matrix, and A inverse is equal to this, then X can be written in the form of A inverse into B. So we have a write this form. So A X is equal to A inverse of B. A inverse is equal to this. B is equal to, you have a minus 4 minus 5 4 3. Then if you just take multiplied by this, you have a minus ka 10, and then you have a minus ka 12, and then plus ka 21, and then you have a 22 minus 22 minus 1, and then similarly we can say that multiplied by this is equal to, you have a 5 by 2, and then you have a minus ka 2, and then you have a plus ka 3 by 2. So you have a 5 minus 4 plus 3 by 2, that is a 4 by 2 is equal to 2, that is equal to 8 by 2. Sorry, 4 by 2, you have a 4 by 2 is equal to 2, and in the similar fashion you can calculate this last one. You have a minus 5 and plus 3 is equal to, you have a minus 2. So that means you can say that the solution of this x1 is equal to, you have a minus 1, x2 is equal to, you have a 2, and x3 is equal to minus 2. This is the solution of a given system of equation. So by this method we can easily find that. Just take a find the inverse of a matrix. If we have to find the, if this coefficient matrix is invertible, then with the help of this we can solve the system of equation by using this technique. X can be written in the form of A inverse into B. Okay, so now this we have to just say that. Now we have a theorem. By this can we state as a theorem without proof. If the n by n matrix is invertible, then for every vector b with the n component, the linear system Ax has a unique solution x is equal to A inverse b. That is the condition is very important. A is invertible. Only this A is invertible, then this theorem is applicable. Otherwise, we cannot use this theorem. Okay, so now we have tried to one more very small problem. In this case again we have a, this is equal to b, and you have a is, you have a clearly a is, you have a simply is equal to minus 2 1, and then you have a 4 and 3. This is 2 by 2 matrix. Then we, you know that if we have a 1 upon AD minus B, A inverse is simply is equal to, if we have 2 by 2 matrix, AD minus BC. And then you have a if you have a AD minus, so you have a, if A is equal to, you have a B C D, then you have a D, and you have a you have a minus B minus ka C, and this is equal to B. We can just calculate the inverse. Okay, just we try to by our method A into identity matrix. So we can write in the form of this is equal to minus 2 1 and 4 and 3. We write 1 0 0 1, and then we have to write R1 can be written as a minus ka 1 by 2 R1. This is equal to, you have a 1, this is we can write in the form of a 1, and that's minus half, and then we have a minus half 0, and then you have a 4 and 3, you have a 0 and 1. Now we have this take a R2 again replaced by R2 plus sorry minus ka 4 times of a R1. So this can be written in the form of matrix is equal to 1 minus half 0, and then this is equal to 4 times of a, this is equal to 0. Then you have a 3 minus this is sorry, this is minus, so the 3 plus 4 by 2 is equal to 2, you have a 5, and then you have a again is equal to 0 minus minus plus 4 by 2 is equal to 2, and then you have a 1. And now this can be written in the form of this. Now 5, so we can write this is equal to 1 minus half, then you have a minus ka half 0 and 1 divided by 1 by 5, so 2 by 5 and 1 by 5. Then we have to get in this. Now we have to R1 replaced by, you have a R1 plus 1 by 2 into R2. So this can be written in the form of a 0 1, and you have a 2 by 5 and you have a 1 by 5, and then we can say that 2 by 5 and you have a 1 by 5, and you just take this 1, the R1 plus this is equal to this. Now we have a, this is equal to, you have a 0, then you have a clearly minus 1 by 2, and plus you have a 1 by 5 because 1 by 2. So this is equal to, you can say that 10, you have a minus 5 plus 1, so you have a minus ka 4 by 10, then you have a minus ka 2 by 5, so minus ka 2 by 5, and then you have to just take into 0 plus 1 by 0 plus 1 by 1 by 2. So we can just say that 0 and plus 1 by 2 is 1 by 10. So this means A inverse is nothing but is equal to, we can say that A inverse is nothing but we have a minus ka 2 by 5 and 1 by 10, and then you can say that like this is maybe we just check this is correct or not. So we just take into this form. This is clearly 0, so this means we can say that minus 10. So this means we can say that clearly you just said this is we have to just check somewhere we have to make mistakes. So we have to just check 3 5 is divided by 2 by 5 is correct up to 2 by 5. Then we have to okay, correct, we have to, this should be the 1 by 2, so 4 by 10. Okay, no problem, this is correct. So just we have a is this form. So this means we can say that if you take a 1 by 10 is outside, then if you take a 1 by 10 minus ka 4, then you have a 1, and then you have a 4, and then you have a 2, then you have a clearly this is equal to into this form. So this is equal to, you can just say that we have a written into this form. Okay, so this means we can say that it means minus 3. This is okay. This is nothing but is equal to, we can write into a inverse of this. We just take somewhere is a mistake or not. We just this is correct. Okay, this is we have to take minus 2. So we just write into the set form. So minus 2 1, and we have to 1 minus 1 by 2 minus 1 by 2 and 0. Then we have 4 3. Then we just take a 4 times of a minus 4 times of a this. So we have a 0, and 3 minus plus 4 by 2 is equal to 5. This is correct. Okay, so this is equal to 2 0 plus 2 and 1. This is correct. Okay, now we just take similarly, we have to take a divide by 5 here, then we have to 2 by 5 and this, then we have to minus 1 by 2. So we have to just take make a 0. The just check is this, you have a minus 1 by 2, sorry, this r1 replace minus 1 by 2, and we have a plus 1 by 2 into 2 by 5. So you have a minus 1 by 2 plus 2 by 10. So this is equal to 10. You have a 5 minus 5 plus 2 is equal to minus 3 by 10. So this value is clearly, you have a minus ka right. We try to writing is this. So AI form means we can write in the form of a, you have a minus 2 1 4 3, and then we try to find the solution inverse of this. Okay, just we try again. We can write in the form of this A inverse. So we just take a, we have a minus 2 1 and 4 and 3, and then we put identity matrix. We have a 0 and 1, and then we have a take a this r1 replaced by minus 1 by 2 r1. So this can be written in the form of a 1 minus 1 by 2, and then you have a minus 1 by 2 0, then you have a 4 3 0 1. Now we have to replace r2 is replaced by r2 minus 4 times of a r1. Then we have a 1, first row is as it is, minus 1 by 2 0, then we have a 0, then you have a clearly, you have a 3 3 minus you have a 3 minus minus plus 3 minus plus 2 is equal to, you have a 5, and you have a 0 minus this is 0 plus 4 by 2 is equal to 2, and then was as it is. Now we just next step is we have to write is a r2 replaced by 1 by 5 of a r2. So this means we can write in the form of a 1 minus half, and then you have a minus half and 0, and you have a 0 1 2 by 5 and 1 by 5, and then we can just take a this r1 replaced by r1 plus 1 by 2 of r1 r2. So this is r2. So we can write this is equal to, we have a matrix 0 1, and then you have a 2 by 5, and you have a 1 by 5, and then we have a 1, and then this is equal to 0. Now this we have to calculating, you have a minus 1 by 2 and plus 1 by 2, and 2 you have a 2 by 5. So this is equal to, you have a minus 5 and plus 2 is equal to, you have a 10. So this is equal to minus 3 by 10, and then you have a 0, and you have a plus 1 by 2 into, you have a 1 by 5. So you have a 1 by 10. So this means we can say that the A inverse is nothing but is equal to, you have a minus का 3 by 10, 1 by 10, and 2 by 5, and 1 by 5, and this can be written in the form of a 1 by 10, and then we can say that clearly you have a minus 3, 1, 2, and sorry, 2 is a 4, and then this is equal to 2. So now you just check, this means we can just say that we have to interchanging this. So by now we have know that the if we have A in the form of a B C D, if invertible matrix, then you know that A inverse can be written as a AD minus BC, and then you can just say that we can write in the form of a this can be written as a D. So you have a minus D, and you have a we can write changing into the this form. Okay, just directly. So you calculate the AD minus BC. So we just try to this method also. So AD minus BC is equal to, you have a minus 10 clearly. So this we can say that this can be also written in the form of, if you take a minus minus also, this is minus, this is minus, this is minus, this is plus. If you put a minus is here, now you clearly say that this means we can written written in the form of a D, and you have a and you have a minus B and minus C. This is the standard way we can write finding the inverse of a 2 by 2 matrices. So this means this way also, this is the same value we have to getting is this simply. Okay, so if we getting the same value for this, this means A inverse is equal to 0, then we have a right hand side is equal to 1 and 2. So we have x is equal to nothing but is equal to, we have to A inverse B. This can be written as a, you have a minus 3, 1, 4, 2, and then you have a 1 and 2. Okay, this is 1 and 2. Okay, just we have to multiply this, and then we getting x is equal to minus 1 by 10, and y is equal to, you have a 4 by 8 by 10, or 4 by 5 is there. So this is the solution of this system of equation we have to getting by using this technique. Now we have to prove some result. This is a very important result. If all the matrices we have to assuming in this is a square matrix of the same size. First is saying that if A and B are invertible, then AB is invertible. So AB inverse is equal to BA inverse. And then this extension is this: if A1, A2, AK and all are the invertible, then their product A1, A2, AK is invertible, and A1, A2, AK inverse is equal to AK inverse, A2 inverse, and so on. If A is invertible, A to the power K is invertible for any K greater than AK inverse is the same as this form. And then if A is invertible, so the transpose is also invertible, then A transpose ka inverse is the same as A inverse transpose is there. Okay, so we know that the method is AB is equal to identity if B is inverse and BA is also identity. For proving this, you know that if we take AB and then we can say that B inverse A inverse, if we prove this is identity, and also we prove that B inverse A inverse into AB is also identity, then by our definition of a invertible matrix, we can say that AB ka inverse is nothing but is equal to same there B inverse A inverse. This is the technique we have to using into this. So with the help of this, we can using the mathematical induction for this case, and then similarly proving this, and then say this is trivial for this one. The third one case is directly come from the 2, and then similar fashion we can proving this result also we using the very basic technique of a transformation. You know that AB ka transpose the same as a B transpose and A transpose, and using this technique we can prove this this thing also. Okay, we start from the first, because A and B are invertible. So I just already say that we have to techniquing this. Now what we do, we have to just take a associativity over this. The A B inverse B, you know that B is also in a matrix, and B inverse B is always is identity, and so this is identity, and A identity is again we have a getting matrix A itself, then this is again you have a identity. So this way we can say that we have to clearly get the identity. Now another way also we took apply from the associativity here. So this is again identity, and this is identity means we have to getting B inverse identity of a B, and this identity of a B is again B. I'm sorry, this should be this should be, you have a B inverse B, and B inverse B is again you have a identity. So this means we can say that B inverse B is also identity. So we prove that B inverse A inverse is equal identity, B inverse A inverse AB is equal to identity. This implies that we can say that AB ka inverse is equal to, you have a B inverse and A inverse. That means always this is true in the case of a two matrices. This means we can just say that the inverse is and we know that the inverse is a unique. So inverse is a unique means we can say that. So we have to show that AB inverse of AB is the matrix of a B inverse A inverse. Now, for the second case, we just prove by the mathematical induction. If we have a1, a2 up to ak to the inverse, then we can say that this is ak inverse and then ak minus 1 inverse and so on. We have a2 inverse and a1 inverse. Now, if we have a k is equal to 1, then we say a inverse. A inverse is equal to itself. This is our claim is trivial. And now for the case of a k is equal to 2, and then if we take a k is equal to 2, this is the previous result. We already proved that we have a a1 a2 ka inverse is the same as a a2 inverse and a1 inverse. This is again trivial, so we can say that a2 ka inverse we have a, this is we can get into this form. So k which is a case 2. K is equal to 2 is the case of a 1. So we can say that clearly this is, now we assume that the assumption is true for k is equal to inductive step is up to k minus 1. So if you say 2k minus 1, then this can be written in the form of a up to this thing. Then we have to try to prove this result is true for any value of a k. So we can write a1, a2, a3 up to a k minus 1. I just write into this, and then we have a k is ka whole inverse. Then by the a b ka whole inverse is equal to, you know that the property is the first part a inverse b inverse. This can be written in the form of a k ka inverse. Then we have a a1 a2 up to a k minus 1 ka inverse by the and by the inductive hypothesis, this is equal to what? This is nothing but is equal to ak inverse. This is ak minus 1 ka inverse and so on up to a2 inverse and a1 inverse. So this means this we say that in this case we can get this solution. So this means we have to just this is true, and then we can just complete the proof of a by the induction hypothesis. We can prove this result is true for all values of a k. Now if in this case if we have a a1 a2 up to ak, we can take a, then we can say that a to the power k the inverse is the same as we have a inverse and so a inverse, this is the k times, we can say that a inverse to the power k. So this is true for the this case is, if we have to prove, then we can say clearly just say that a1 a2 ak. So we can say that a1 a this ka inverse we take, this is nothing but equal to k times, this can be written as a to the power k ka inverse, and then by the this property can be written as a inverse up to a inverse. This is also is a k times, then we can say that this can be written as a inverse to the power k. So this proof is complete by the previous result. And now last one is we have a ka trans we can establish the formula the same, showing that by this. So we can just say we know that the method for a b ka transpose is the same as a b transpose a transpose. So we take a technique is a and we have to show that a transpose inverse is equal to, we have a inverse ka transpose. So we just take a in the form of a inverse ka transpose, and then we can say that a transpose is equal to identity, and we have to show that a transpose a inverse ka transpose is also identity. Then we can say that by the our definition is, so we starting from this a transpose and a inverse ka transpose, but you know that this can be written as the we have to write this is equal to a inverse ka this is transpose. We just take the better we can write into this form. This can be written in the form of a, we just try to this form, we have to write into this form. So a transpose, and then we have a inverse ka transpose. This can be written as a inverse a ka whole ka transpose. This identity ka transpose, this is equal to identity. And also we can just take a inverse ka transpose and then a ka transpose. This can be written as a inverse ka whole ka transpose is again identity ka transpose is equal to identity. So in both the cases we getting a transpose a inverse ka transpose is equal to identity is equal to, we have a inverse ka transpose A transpose. This means we can say that by these two property, again we can say that one of them inverse. So A transpose ka inverse is the same as A inverse ka transpose. This is complete the proof of this result. So this means we can just complete the proof of this result. Okay. Okay, now we have a problem. If we have suppose B is an invertible matrix and A is any matrix AB is equal to BA, then A and B inverse is commute. Then we have to show that the A and B is commute. So we can say that multiplied both sides by B inverse. So we can getting AB B inverse this. Then you can just apply here the A B inverse. You have a B times A B inverse. Then you can getting here the A is equal to, you have a B and sorry, this is we just writing this. Then we can write into this means A B inverse is equal to B inverse. And now B inverse identity, then A can be written as a B inverse. And then again we have to multiply it by B. So B inverse. So we have to just B inverse A can be written as a B inverse B, and then you can just write into, sorry, this can be written in the form of this. Now we have to write in this a form of a B inverse B and A of B inverse. Then this can be written identity A of B inverse. This is nothing but is equal to, we can say that A of B inverse, then B inverse A is equal to AB inverse. This complete the solution of this problem. Now I just prove one more result. There is all the parts. This is we have to just say that if we have A is an n by n matrix, then the following statements are equivalent, and that is are true for all or all are the false. If A is invertible, then we can say that Ax is equal to 0 has only trivial solution. If A is invertible, then a homogeneous system has only trivial solution. Then the reduced row echelon form of A is identity form. If A is invertible, then always reduced row echelon form is always identity. The system of any system Ax is equal to B has at least one solution for X for every choice of a column B. So we have this thing. So there exists an n by n matrix C such that AC is equal to identity. If there exists another matrix, by the definition, if A is invertible, then there exists a matrix C, then C is equal to identity matrix. So we have to try to prove this. Is we have to imply like this: all are equivalent means A implies B, and then we show that B implies you have a C. Then we have to C implies equal to D, and D implies is equal to E, and then E implies we have to just say that is equal to A. Then we have to say that this each and every one is equivalent to each other. So this means this is the we prove the equivalent into this form. We prove that A implies B, B implies C, and C implies D, D implies E, and E agar implies it, then we have a whole circle is there. So if you see the by the circles, we can say starting from the point A, then we get B is equivalent, and B is equal to C equivalent, C is equal to D equivalent, then D is equivalent to, we have a E, and E again F. So we have to moving into this form, and then we can say that this all are equivalent. So A implies B. Then if we have A is equal to, A is an invertible matrix, then Ax is equal to 0, then X is only trivial solution are there. Assume that A is invertible and X not be any solution of this. If any solution of this means we have Ax is equal, Ax not is equal to 0, and because A is invertible, we can write A inverse Ax not is equal to A inverse 0, and we have a 0 matrix, then we can say that this can be written as A inverse A, and you have a X naught is equal to 0 matrix, then this is equal to identity of X naught is equal to 0, implies that X naught is equal to 0, then there is a trivial solution. That is, the proof is very trivial. So we can say that this is inverse, then we can say that X naught is equal to 0, then the system has only trivial solution. If A is invertible matrix and Ax is equal to system is homogeneous, then we have only the trivial solution. Okay, now we have if the system has a trivial solution, then we have to try to, this system is a trivial solution, then this can be written as a row echelon form is always in the form of a reduced echelon form with the identity form. So we have a Ax system, this system has a this system Ax is equal to 0, then what is the, we can write the argumented matrix of this. If this system has it only trivial solution when X is equal to 0, Xn is equal to 0 after the Gauss elimination reduction method, substitute for any this, we getting this is the solution for matrix this system. Now we write the argumented matrix is the after reducing this because is a trivial solution. The only trivial solution means this system is after reducing all the system of this can be reduced into this form, and all the right hand side is equal to 0. If your right hand side is equal to 0, then you can say this is ax form. This is the dealing the last column 0. So discarding this last column 0, show that the reduced echelon form is A is nothing but is equal to, you have an identity matrix. So this completes the proof of the second part. If Ax is equal to 0 is a homogeneous system, what we do, we have to just write is this, and because this system has a only trivial solution, then we have a, if it's a trivial solution, this reduced echelon form should be into this form, and if in this form, then this is nothing but is equal to identity matrix. So this is true into this one. Now we have to, if the system has a is identity form, then we can show that this is equal to x is equal to c exists, then this is a solution. So consider the argumentative matrix A and B, the system of Ax B. Since A is an identity matrix by the C, so same operation we have to applying operation, we can converting this matrix into a identity into C, the sum column of C, hence the system has the solution x is equal to C. So this means D is whole. If we have a because we argumentative matrix this, then because we have a is always is identity matrix, so after elementary row operation we getting identity into some new matrix is a C, and that C is equal to, we have to getting is nothing but x is the solution of a this matrix C. So this complete the proof of the C into D. Now we try to D into E. We write In is the identity matrix E1, E2, En, where E1, E2, En we have the column of identity matrix. We have this means we can say that 1 0 0 0 0 1 0 0 and so on like this. Now for j running 1 to n, the system Ax is equal to Ej has a solution of Cj. So Ax Cj is equal to, you have a E of j. We can write, and then C is equal to what? We have a C1, C2, C3, all the column. Then we have to multiply it by this is equal to AC1, AC2, ACN, and then AC1 is equal to, you have a E1, E2, En, and this is the identity matrix. So this is prove the E. So we can say that this is AC is nothing but is equal to, you have identity matrix. If C is this complete the proof of the this D to E. Now E to F is very trivial. We have a AC is equal to identity matrix, then Cx is equal to 0, implies that x can be written in the form of identity into x, and then identity you have a AC. So this is AC is you have a already Cx is equal to 0, so this matrix 0, A0 is equal to 0, so this means x is equal to 0. So the condition to use to hold for a matrix for a C, and that means this complete the solution. So by the previous implication, A implies C, there exists a matrix C dash, C dash is equal to, we have a case in the identity. Then we can say that A can be written as a identity, and then is equal to C prime. Therefore, we can say that clearly, we can say that CA is equal to identity. So A together with AC is equal to identity, they show that C has an inverse. So we can show that we can CA and we have a this is C prime is equal to identity. So we can say that then A has an inverse. So this means A is first is whole. This completes the proof of this theorem. And now I think I have to stop this lecture at this point for we have to complete this solution, and then with the help of this we also try some problem in this thing. So thank you very much for